Okay, so let's not do homework questions today, and let me just finish principal stresses, and then I'll be happy to answer homework questions on Wednesday. So we're going back to principal stresses. Oh, wrong kind of principal. And the idea of principal stresses was for a given stress tensor, we're looking for the inclined faces, looking for faces, and these are not, like, generally speaking, these are not the faces of the stress cube. These are at some kind of weird angle. We're looking for the faces where the traction vector is parallel to the outward facing normal. Outward facing unit normal. So that's what we always call n hat. And when we find these, what we've found, so these are faces with only normal traction components. Okay, so what we ended with last time was we had this equation that said, we derived that this is what we need. We need to satisfy this equation where sigma xx minus lambda, and then sigma xy, sigma xz, sigma xy, and then the quantity sigma yy minus lambda, and then sigma yz, sigma xz, sigma yz, and then finally sigma zz minus lambda. Times this unit normal, this unit vector, nx, ny, nz, is equal to zeros. And to get a non-trivial answer, we have to set the determinant of that matrix equal to 0. So the determinant of, I guess I'm going to write it again. Looks like I am. Sigma xx minus lambda, sigma xy, sigma xz, sigma xy, quantity sigma xx minus lambda, sigma yz, sigma xz, sigma yz, and the quantity sigma zz minus lambda. Determinant of that matrix is equal to 0. Yes? Yes, it should. Thank you. So the way you calculate the determinant of this matrix is you can go a couple of different ways, but I'm going to go, so it's going to be this times the determinant of this little 2 by 2 matrix minus this times the determinant of cross out this and the determinant of that little matrix plus this times the determinant of this little matrix. I'll just give you the formula, but what? It's like how you do the cross product, yeah. This is sigma xx minus lambda times the quantity sigma yy minus lambda times sigma zz minus lambda minus sigma yz squared minus the quantity sigma yy minus lambda times the quantity sigma xy times sigma z minus lambda minus sigma xz sigma yz and then plus, this is all one line, sigma xz times the quantity sigma xy sigma yz minus sigma xz times the quantity sigma yy minus lambda, and set that equal to 0. Yes?
The second one is supposed to be sigma xy instead of sigma y.
The second one is supposed to be yes. Thank you. Minus sigma xy times, and that other stuff looks right, and then, yeah. Okay, so what does it mean to find the roots of this equation? So all the sigmas are given. So we're looking for lambda values. This is a cubic polynomial. So there are 3 roots. And for each of those roots, there is a corresponding unit vector n. Okay. So that's the idea. The roots are, these are called the eigenvalues, those lambdas. And in this application, those are the principal stresses. These unit vectors are called the eigenvectors. They're mutually orthogonal orthogonal. So they're all perpendicular to each other. And together, they tell you the coordinate system where this thing happens that we're looking for. So together, those three give a coordinate system with only normal stresses. So in practice, how do you find these? Well, on a TI 89 or Inspire, you use the command EIG, those are all lowercase, and then capital V lowercase l of the matrix. Okay, this is the original stress tensor. And it gives you a set of values, sigma 1, sigma 2, sigma 3. And then if you use the command EIGVC of that matrix, it gives you a matrix that's like N1x, N2x, no, that's exactly wrong. N1x, N1y, N1z. That's the first eigenvector that corresponds to this one. Then N2x, N2y, N2z. That corresponds to sigma 2. And N3x, N3y, N3z. And that corresponds to, so these two correspond, these two correspond, and these two correspond. The lambda? VL gives you magnitude. Yes, and so if you make a coordinate system out of, so if you use plus or minus N1, plus or minus N2, and plus or minus N3 as coordinate system axes. Okay, so this is your new x-axis, y-axis, and z-axis. Okay, and the plus and minus are just to make sure that it's a right-handed coordinate system, because you have to have a certain relationship between x and y and z, z and x, right? X cross y has to be equal to z, y cross z has to be equal to x, x cross y, x cross z has to be equal to negative y. Then the new stress tensor is sigma 1, sigma 2, sigma 3 with zeros everywhere else. Cool, right? Now, if we call, let's say sigma max is the maximum of those three. Sigma min is the min of those three. And sigma mid is the third one, whichever one isn't a max or a min. Okay. Now identify the axis corresponding to sigma mid. Okay, so each of, this is 20, this is 5, this is 8, say, okay? So 20 is the max, 5 is the min, and that means the middle one is the z axis, okay? Then if you rotate your coordinate, so now rotate the coordinate system plus or minus 45 degrees about that middle axis. It'll give you a stress tensor with the maximum absolute value of shear stress. And absolute value, tau max, is going to be equal to sigma max minus sigma min divided by 2. So if you need the whole stress tensor, you can do it with that matrix transformation. If you only need the value, you can just use that simple formula. And knowing what that maximum shear stress is a really important thing for determining when something is going to, reach different stress limits associated with breaking, Okay, so let's do an example. And we'll do it with a calculator, and we'll also do it by hand to see how it works. So let's say we have this stress tensor -5, -2, 0, -2, 0, 0, 0, 0, bless you, -10 in megapascals. And we want to know sigma max, sigma min, and tau max. All right, well, the way we're going to do this is we're going to set up this. So the requirement is that we have the quantity 5 minus lambda, -2, 0, -2, 0 minus lambda, 0, and then 0, 0, -10 minus lambda. And we're going to set the determinant equal to 0. That's how you avoid getting the trivial solution to this. And that gives us this polynomial, the quantity 5 minus lambda times negative lambda times negative 10 minus lambda minus 0. And then minus negative 2 times the quantity negative 2 times the quantity negative 10 minus lambda minus 0 plus that's 0, so that's it. And if you multiply that out, hopefully I did it on this page. No. So we have 5 minus lambda times, if I multiply all this together, we have 10 lambda plus lambda squared. And then we have plus 40 plus 4 lambda, I think, is equal to 0. And now we can FOIL this one out. So we have 50 lambda plus 5 lambda squared minus 10 lambda squared minus lambda cubed plus 40 plus 4 lambda is equal to 0. Did I do that multiplication right? Well, that's not a good example to use. So what do we get? Negative lambda cubed. And here are our squares. Minus 5 lambda squared. And then here are our linear terms. And then I was hoping this would come out with no constants, because then we could factor one out and use the quadratic formula to solve this. But that's not what we see here. So what am I going to do here? Okay, so yeah, can somebody solve that? Square root of what? Say that one again.
Negative times
square root of 41 minus 5.
Yeah, square root of 41.
Oh.
And then minus 5. And all that in parentheses.
Like that? Okay, those are the 3 roots. Those are hideous. This is not a good example. I need to come up with a better example than that. What? It's inside is plus? Is this plus or minus or just? So this is negative, but this is plus or minus?
No, that's when it's outside.
And plus inside.
Yeah.
Okay.
Well, if there's a minus, then it's minus 5. Okay.
Yeah. Okay. Let us never speak of this one again. Okay, I'm going to come up with a better one instead. I can't really do that because of what the next step is. Okay, so here's what I'm going to do. Okay, let's start this over. Okay, so this is all like behind the scenes. Pretend you don't know. Okay. So let's say that the principal stress tensor that we want to come up with is 10, -5, 0. Okay. And now let's just rotate this randomly. So we're going to get a coordinate system that, we're going to come up with a stress tensor that's not principal. Okay. So let's rotate the coordinate system plus 20 degrees about the y-axis. It doesn't matter. This is just a random rotation. Okay, so our rotation matrix Q is going to be 0.940, 0, -0.342, 0, 1, 0, positive 0.342, 0, positive 0.940. Does anybody have that programmed in? Can someone do that rotation? So we're going to go, so if I call this, I'm going to call this the principal stress tensor. And the one that I'm looking for is going to be Q times this principal stress tensor times Q transpose. Okay.
Should it be all principal stresses still?
No.
Oh, yeah. It's 8.83, 0, 3.21.
What was the third one?
3.21.
Okay.
0, -5. 0. 1.698.
Okay. So what we have here is, so we have a stress tensor that's not principal, but what we should get when we find the principal stresses for this, is we should get 10 and -5 and 0, and the axes we get should be rotated 20 degrees about the y-axis. Okay. Anybody have any questions about why that is?
Can you just relate the stress tensor to the first one we have now?
Yeah. So whenever you change the coordinate system, your stress tensor values change seemingly at random as far as we can tell, But we haven't changed the actual state of stress. We've just changed what orientation we're looking at it with, okay? And now we're going to calculate the principal stresses, which is basically saying, now find a way of looking at, so now we're looking at this from a random angle. But now it says, find a way of looking at this thing where all you have are principal stresses. And so it's going to put us back in that original orientation. Okay. Okay, so now here's the problem. Here's the example problem. So for this stress tensor, 8.83, 0, 3.21, 0, negative 5, 0, 3.21, 0, 1.698 megapascals. We want to find sigma max, sigma min, and max shear. Okay, so we need to find the determinant of, or we need to find the lambda values where 8.83 minus lambda, 0, 3.21, 0, negative 5 minus lambda, 0, 3.21, 0, 1.698 minus lambda, 1.1698, okay? Well, let's round that to 1.17. And we're going to set that determinant equal to 0. So this gives us the polynomial 8.83 minus lambda times negative 5 minus lambda times 1.17 minus lambda minus 0 plus 3.21 times 0 minus 3.21 times negative 5 minus lambda, and all this is equal to 0. So this is 8.83 minus lambda times, I'm going to FOIL out the inside. So what's negative 5 times 1.17? -5.85. And then plus 5 lambda minus 1.17 lambda plus lambda squared. And then what's 3.21 squared? Okay, so negative 10.304 times negative 5 minus lambda. And this is all equal to 0. Let's simplify a little. So we have 8.83 minus lambda times the quantity, negative 5.85 plus 3.87 lambda plus lambda squared. I guess plus 10.304 times negative 5, or 10.304 times 5. 51.5. Am I losing you? 51.52, and then plus 10.304 lambda, and that's equal to 0. We're so close to having, so all we have to do, our last painful thing we have to do is FOIL out this, well, you know, distribute this first thing. We're gonna, so it's okay if we get a cubic as long as there's no constant term, because then you can factor out, you know, one of the answers is going to be 0. So what's 8.83 times negative 5.85? 0.65? The 5 is continuous? Okay. And what's 8.83 times 3.87? 34.17 lambda plus 8.83 lambda squared, and then plus 5.85 lambda minus 3.87 lambda squared minus lambda cubed plus 51.52 plus 10.304 lambda is equal to 0. And you can see that those cancel if you're a naturally sloppy person. Okay, so what do we get? That's what we needed, those to cancel. So we have, there's our cubic. Our squares are here. Our linear terms are here. And so we get negative lambda cubed. What's 8.83 minus 3.87? So plus 4.96 lambda squared. And then what's 34.17 plus 5.85 plus 10.304? 50.324 lambda is equal to 0. If I pull out I'll pull out one negative lambda, and we get lambda squared plus 4.96 lambda plus 50.324 is equal to 0. One of our roots is 0. The other one we can get with what? Yes. These are both minus, right? Yeah, you never have to do this, right? But I just want you to, and it's not this step that I want you to see, it's the next step that I want you to see, coming up with the eigenvectors. But I think this is one of those things that's useful to do once and then never do again. Okay, so can someone give me the roots? Okay, so 0, negative 5.035, okay, and then 9.995. So this is our -5 that we started with. This is our 10 that we started with. We didn't get it exact because everything's rounded, you know. Okay. So now, how do you come up with the eigenvectors? Usually, by the way, in practice, these are all that matter to us. But if to get the eigenvectors, that tells you the orientation of this principal coordinate system. And so like it could be useful. It just usually you're not looking for those. But now we want to find the eigenvectors. And so what we're going to do is one by one plug the roots for lambda into the eigenvalue equation and solve for this unit vector n. Okay. So first, let's do it for the let's do it for lambda equals 0. Okay. So we're going to plug that into our eigenvalue equation. Well, the eigenvalue equation, if we go back to the original problem, says plug. So we're going to plug the 0 in for lambda. Okay. And we're going to have this matrix times that unit vector is equal to the 0 vector. And we're going to solve for those n's. So 8 point, okay, so I'm taking this. And what we're going to solve is this, with 0 in place of all these lambdas. Okay, so and so the first equation, if you do the matrix multiplication, you get 8.83 nx plus 3.21 nz is equal to 0. Okay. The second equation, you get that -5 ny is equal to 0. And the third equation, you get 3.21 nx plus 1.17 nz is equal to 0. Okay. So what does this tell us? So let's say that for now, let's choose nx equals 1. Okay, what does that tell us about nz? So we have 8.83 times 1 plus 3.21 nz is equal to 0. So nz is equal to negative, what's 8.83 divided by 3.21? Let me guess, 0.940. No, 0.342. Oh no, it's not going to be that yet. We're going to have to 8.83 divided by negative 3.21. 2.75. Okay, so we have this vector now that says, so our n is equal to 1, 0, negative 2.75, but it's not a unit vector. Okay, so now normalize it. And you get, divide everything by 1 squared plus 2.75 squared square root. And I hope what we're going to get is 0.3420, negative 0.940. Okay, so that says that the coordinate axis, the axis of the new coordinate system, corresponding to the principal stress of 0 is plus or minus, it can be either direction, 0.3420, negative 0.940.
It seems like you just arbitrarily chose the x.
Yeah, so there's always redundancy in this system. These two are always going to be, there's always going to be two that are linear multiples of each other. So just you can just choose some arbitrary value and then normalize it at the end. It looks like we have 3 equations for 3 unknowns, but it's really only two independent equations for 3 unknowns. Okay. All right, so that's the first one, and you can see, like, why did I know these were going to be 0.342 and negative 0.94? Because at the start of this, the way I got our coordinate system was I started with a principal coordinate system and then did a 20-degree rotation. And so what we have here, cosine and sine of 20 degrees. Okay. And when we do so I'll finish this on Wednesday. I think there are problems you should be able to do before I finish this. But we're going to do it now for the 2 other eigenvalues. And what we're going to get are unit vectors that are perpendicular to that one. And so we'll have 3 vectors that are all perpendicular to each other. We can make a coordinate system out of them. And they're all rotated 20 degrees about the y-axis from our original.
And then we get the values that we want in the first place.
Yeah, so we already got the values when we calculated those eigenvalues. That's the step you have to do first. And then from those, this is the 0, negative 5, and 10. And then from those, you can decide which one you want to represent your x, your y, and your z. You can choose any order you want. So as soon as we got this, you could just say, okay, my principal coordinate or my principal stress tensor is 0, -5, 10 along the diagonal, and that's the end of it. All the rest of it is just to figure out the orientation of that new coordinate system relative to the old coordinate system. Okay. Yeah. So I guess the main thing that I want you to remember about this is with a calculator or with Wolfram Alpha, all you do is put in the original matrix and it spits out the values you need. Okay, so all this stuff we're doing, you're not going to have to do that, but you know, to do it by hand, I think is helpful for just getting a better sense of how it all fits together. I think but we won't do this very often. Okay, that's all.